Welcome everyone. Today in this video I will go over what linear approximation is, and I will use an example to demonstrate how we can use it. So to do that, as usual, I will draw a coordinate plane with x and y as usual again, and let's say that we have an arbitrary function. So it's with a graph like this. The key point to understand linear approximation, the idea behind it is that if you zoom in this point, let's say this point with x value x naught, if you zoom in this point, maybe as you get closer, the curvature here, the curvature there, maybe it will start to look like this, and as you get closer and closer, it will look like this, and at some point it will look like as if it is a line. All right, so you can think of this as take the curvature of Earth, for example. We know that the Earth is a sphere, but when we are on it, we see it as if it is flat, even though it isn't. Why do we see it as if it is flat? Well, because we are too close to it. It is a huge planet, and we are too close to it, so it appears flat, even though there is a curvature. So just like that, in this case, and for any function, when you get closer and closer to a curvature, it will appear flat, it will appear straight, it will appear as a line. So that is where linear approximation comes in place. So let's say that we zoomed in on this region, and we now see a line, a thing that appears as a line. This is what we see. And we are still at x naught. This is our focus point. This is where we zoomed in. And maybe we have another point x here. All right? And notice that x and x naught are very close to each other. It is not like x is equal to 100 and x naught is equal to 50. It's not like that. They are extremely close to each other. Maybe this is 9.1 and this is 9.1001. That is how precise I'm talking about. Or you could say like this as well. It doesn't matter, but they are very, very close to each other. So let me erase the example. All right. So if we wanted to calculate the slope at x is equal to 0 at this point, I mean x naught, not x is equal to 0, at the point x naught. Oops, what did I do? Anyway, so how could we do it? Well, using the definition of slope, we would say that it is simply delta y over delta x. And we would say this is the slope. But if we want to bring derivatives into play here, if we want to include them, we can say this is equal to the derivative. And if you are not familiar with derivatives, a derivative just means the slope of a function at some point. In this case, this is function f of x, and when we put this little thing here, it means its slope at x naught. It will be equal to this, but I know you're saying not equal to. We will need to take delta x's limit as it goes to 0. So since we don't do that, this isn't equal, this is just approximately equal. And surprise, this is actually linear approximation. Approximation. I hope I didn't spell it incorrectly. Yep, I got it right. This is linear approximation. Let's expand this a little bit and make it a more useful formula. For delta y, we can write f of x minus f of x naught, right? This is our y coordinates, and we just plugged in the values to get f of x minus f of x naught. And I will erase these coordinate system to not make it confusing, because we zoomed in, don't forget. Right? This is this region zoomed in 1,000, 1,000,000 times. Anyways, and for delta x, we just have x minus x naught. This is approximately equal to the derivative at point x naught. And if we want to solve for f of x, we will say it is approximately equal to, we multiply both sides by x minus x naught. So we get this, and if we add f of x naught to both sides, we are done. This is the equation. This is approximation for linear approximation. So this is it. And I want to just do a quick example about this to show how it can be used. So we have example here. Let's say that you are being asked to find the square of 11.1. Yep, you are asked this, what is the value of this? And you don't have a calculator, or you are not allowed to use a calculator. How would you give your best approximation? Right? How can you get as close as possible without using a calculator? Well, the first thing you need to do is you will say, I will model this as if I have a function which is x squared. And I am just being asked about the value of this function where x is equal to 11.1. So I will use linear approximation. How can I use it? Well, if you look at the formula here, you see that we need an x naught. We need a starting point to base our approximation on. And the best starting point will be a point that is close to the point of interest. So which point is close to 11.1? Well, you could say, all right, let's choose it as 11.11. It is very close to it, but can you take the square of this? I mean, it got even harder, right? So you need to take a reference point which is easy to evaluate with the given function, which brings it to the obvious, perhaps for some of you, but it might be tricky as well. It brings us to f of 11, because we know that 11 squared is equal to 121, or you could just multiply it and see. It is not that hard to multiply. So we got this. And now we can use the linear approximation. So this is x naught, by the way. X naught is equal to 11. And 121 is simply f of x naught. So I am just writing the formula. If we had f of x is approximately equal to, so f of 11.1 in our case is approximately equal to the derivative the derivative at x naught. Well, what is the derivative of x squared? It is simply using the power rule. It is equal to 2x. We bring the exponent forward and decrease it by 1. It is equal to 2x. So it is equal to 2 times 11, or 22, at x is equal to 11, which is our x naught in this case. Times we will have x minus x naught. Our x was 11.1 and our x naught is 11. Then we have plus f of x naught. And what is f of x naught? Well, we have said it here. It is 121. So let's write everything. And for f of 11.1, we will simply write the square of 11.1, because that's how we defined f. And here we have 0.1. If we multiply it with 22, we have 2.2 plus 121. So we get 123.2 as our approximation for the square of 11.1. Well, how close are we? What is the actual square of 11.1? If you use a calculator, which I am doing right now, you will see that it is equal to this. It is incredibly close. It is incredibly close. If you were to, do a percent error check on this, you would, when we say percent error, well, you would quickly do this. And if you don't know this formula, I can go over this in a future video. I would actually love to go over this. And if you do that, you will just have, let's see what we get. You would have a percent error of 0.008%, which is incredibly small, of course. So this is it for this video. I just talk about linear approximation and gave an example to demonstrate how it can be used. And in the next video, I plan to use it to prove a very, very useful theorem. Not a theorem, actually, very useful formula, very useful approximation. And I will actually tell what we will prove in the next video. We will prove that if we have this thing, this is approximately equal to this. You might have seen this before. This is correct as epsilon approaches 0. And in the next video, I will go over this. So stay tuned. And I hope you enjoyed this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.